All right, welcome everybody. Apologize for the delay. Thanks for sticking with us. Hopefully you can all hear me now. If there's any trouble with the audio, please type a question or raise your hand, and if you want to speak, you have a microphone, you can turn your microphone on and ask a question directly to the rest of the audience. Today's discussion is about optimization. Perhaps I could, I hope everybody's paying attention. Sometimes it's a little hard. I apologize for the 10-minute delay. Today we're going to talk about some of the optimization methods that are in SciPy, included in the nthought distribution. I hope that if you have questions, you won't hesitate to use your interface to raise your hand or get our attention with a comment in the GoToMeeting interface. You can type a question or chat, and we'll try to answer your question directly. Or if you'd like to speak, you're welcome to speak and ask a question directly by turning on your microphone and raising your hand, and we'll unmute you. I'd like this to be somewhat interactive, if it could be. I understand it's a little awkward. We're talking over many miles and over a computer interface, and sometimes it's more convenient just to listen to me chat on and on. But I do want to be directed by your questions, and I can answer your questions directly as they come up. So today we're going to talk about different kinds of optimization, and I'm going to give a summary and then show some examples basically of using all of the standard or basic optimization methods that are inside of SciPy. There's two basic kinds of optimization you'll encounter. The first is sometimes called unconstrained optimization, and this kind of optimization you try to find, you maximize an objective function. This objective function might take many variables. X, as shown in this slide, could be one variable, it could be a million variables. If you are solving a million variables successfully with SciPy, I'd love to hear about that. You can do up to thousands of variables with, depending on the objective function. So f is a function that takes a vector x and returns a single scalar value in the real plane, in the real line. And then the optimization method searches around varying the inputs until it finds the best answer that it can find using different approaches. And then that optimal answer is returned as the optimization solution. All of these methods really are doing local optimization. In other words, they all start from a guess, a position that you think the optimum is near, then they search around that position until they find the best answer. Now, if there's a local area that's smaller than the rest, then it'll find that solution, and it won't find the other global solution, which might be farther away. There are global optimization methods, and there are basically toy global optimization methods inside of SciPy. But really, global optimization is a more difficult problem. You basically have to, one simple approach is to sample all over the space and then find the local minimum at each of those spaces, and then pick the smallest as your global answer. So constrained optimization is fairly simple. It's been around for a long time. There's lots of different methods for doing constrained optimization, unconstrained optimization. Constrained optimization is newer, and more techniques for doing constrained optimization come out basically every year. A lot of these are in commercial codes. In SciPy, we do have thanks to the generosity of several volunteers, we have constrained optimization methods that we'll talk about. In the constrained problem, you solve exactly the same thing. You're trying to vary the input x until you get a value that's as small as possible. But on the other hand, you can add additional constraints, such as bounds constraints. So the input variables are going to be between a lower and upper bound. You can have equality constraints, which can always be written as a series of functions that, when given the input value, have to equal 0 at the solution. So every input, the equality constraint has to be satisfied at the optimum. And then you have inequality constraints, where another set of functions that can always be written as taking the input vector and returning something that has to be bigger than or equal to 0. And there could be an arbitrary number of these equality or inequality constraints. So that's the general constraint problem. And there really is only one method in SciPy that handles that general constraint problem. There are several methods that handle parts of the constrained problem. So one thing to say about optimization before we start talking about some of the methods in SciPy is there is no magic bullet. Optimization is kind of an art form because it really depends on your problem as to which method is going to work best for it. Really the landscape of the objective function and what it looks like. You have a lot of little narrow peaks a lot of wide? Does it have narrow peaks, narrow valleys? Are they very elongated like a banana, or are they very bowl-shaped? So that's why different optimization methods have emerged, and why it's always useful to try a couple of them if the first one doesn't succeed. And then there are general principles that are used throughout. One of the general principles is that we basically apply Taylor series approximations to the functions, and then try to locally optimize a parabola. At least several of the methods do something approximating that kind of approach. There is, I don't have a slide for this, but I will talk about, when you're talking about unconstrained problems, unconstrained methods, there really are two approaches, and then generalizations of these approaches typically apply to the constrained problem. One approach is called a line search approach, and the other approach is the trust region approach. Of course, there are additional stochastic approaches, particle swarm methods, that sort of thing. We don't have some of those inside of SciPy yet, so I won't be talking about those. We also don't have trust region methods. And the difference between a trust region method and a line search method is in the line search method, you basically pick the direction you want to minimize. So you have a starting point. You pick the direction you want to go next. And then you try to find the optimum step to jump in that direction to get to the next guess. And then you iterate on that process. The trust region method, instead it first picks a ball shape, or an optimum ball, or an optimum region or radius to find the optimum solution in, and then it solves a little mini optimization problem and finds the lowest point inside of that region. So therefore it finds the direction to jump in that number of, or that unit of distance in order to find the next minimum. There aren't any trust region methods in SciPy, but those can be a useful approach to take if your problem is not amenable to some of these methods that are currently in SciPy. So the unconstrained methods in SciPy that we're going to talk about are the Nelder-Mead simplex method, the Powell method, and these only require the function, and they only use the function as well. So even if you have the derivative, these methods won't use that derivative information. They each have, I know a little bit about the Nelder-Mead simplex method. The Powell's method I'm not as familiar with, or I was at one time and I've forgotten now how it works. But I'm not going to give an explanation or go into detail about how these different methods work, only to say the simplex method basically just evaluates the function at points. If the maximum point, a simplex is basically a polytope. It's a triangle in 2D, a tetrahedron in 3D, and that sort of thing. It's n plus 1, where n is the dimensionality of the problem. If I'm finding 3 unknowns, then it finds a polytope. It has 4 points that evaluate that. The very biggest point, it reflects that through the plane or the subspace defined by the other points, and finds another point, and tries to keep reflecting this polytope until it finds a minima. That's the simplex method, and it's very handy. It's a workhorse. If you just have the function, you can give it to this method and try to find an answer. And a lot of times it's fairly successful if your problem is generally well behaved. The other approaches, the Broyden-Fletcher-Goldfarb-Shawano method, or BFGS, and the conjugate gradient method, CG, as well as the Levenberg-Marquardt method, although I won't talk about this in this context because its interface is slightly different than the others. But the BFGS and the CG methods both use the gradient. If you have it, you can provide it, and then you can use the exact gradient. If you don't have the gradient, then it will approximate a gradient using first differences. But still, the algorithm needs a gradient, and it will use an approximate or an exact gradient, depending on what you provide. And then it will proceed to use that gradient information to find the steepest descent direction and go in that direction a certain amount each iteration. Finally, there's one method inside of SciPy called the NCG method, which uses a Hessian. And it can use the Hessian if you provide it. If you don't, it will calculate the Hessian basically using approximations on the supplied gradient. So you do have to provide the gradient in order to use the Newton conjugate gradient method. So here's a simple function. It's called the Rosenbrock function. And you can see that it's defined if I have n variables in this vector x. This is what it evaluates to compute the function. And it's defined for any number of n. So basically it depends on what kind of vector length you put into this function as to the dimensionality of the problem. I'm going to use this function just to illustrate how to call and how to use several of the optimization methods. So I'm going to go over to a Python prompt now. And I'm going to bring up an editor window that has some examples of using constrained optimizations. So basically, I'm importing a few things from NumPy, but in particular, I'm importing scipy.optimize as opt. So that's where all the optimization algorithms live, is in scipy.optimize. So scipy.optimize as opt, and now I have, if you hit opt.tab inside of an IPython shell, you can see all the different methods that are there. All of the methods we're going to talk about start with fmin, and then they either end there or have an underscore additional name associated with it. So we've talked about fmin, fmin vfgs. We're going to look at fmin cg, fmin ncg, fmin powell, and fmin, that's all, vfgs, cg, fmin, and fmin powell. If I look at the help docstring of fmin, it shows me the calling signature, basically. And you can use this. All of these functions basically have the similar calling syntax. You call fmin, and the first argument you give to fmin is a function or a callable. This is a thing, a Python object that can be called, and the first argument to that function that can be called, x right here, has to be the vector that's going to be varied in order to minimize the output of this function. One of the second arguments that's always required with all these minimization algorithms is an initial starting guess. So you have to always put, where am I going to start this optimization process? And the optimization process evaluates the function, does some kind of a local searching to find the next iteration, goes to that position, and gets another value of the function and sees if it's better or worse, and depending on what it is, updates the next iteration and successfully tries to find a minimum. And there's a bunch of different ways to do that. So it's pretty simple to set up an optimization problem in SciPy. Here is the unconstrained problem. I'm going to start most of these from the initial position of 0, 0, 0, so the 0 vector. And here's the Nelder-Mead simplex, or calling the Nelder-Mead simplex algorithm. A couple things to note. One is I'm also passing to the fmin function a full output equals 1. If you look at the docstring for fmin, it's a little confusing at first because of all these extra arguments. If you just focus on fmin and what has to be provided, func and x0, it's a little bit easier. The other thing that's useful to note is the args equals. And quite often you have a function defined which, besides taking the vector to be minimized, it might take additional parameters or additional arguments that are just going to be fixed throughout the minimization, but it's convenient to include them in your function call. And these can be passed each time through the iteration in this args parameter. So here's the approach, and then there's several other parameters. And each of the different minimization algorithms have additional parameters, and they're all slightly a little bit different. Typically, you'll find parameters like the tolerance for when it's finished. How do I know what kind of change in the x distances and the distances of the various components of x have occurred, and when do I say that I'm not really changing much, and so I'm going to say I'm at the minimum. Or what's the tolerance in the value returned, and so if the two values are within 10 to the minus 4 in this case, the algorithm is going to say these are the same. There is a way to stop the iteration, max iter, and several of the algorithms will have a maximum iteration flag. They're not always spelled max iter, but there'll be some keyword that allows you to specify how many times am I going to go through the basic iteration of this algorithm. And it's useful because there's always something. In this case, it's none, meaning it's going to use internally a certain number, typically based on the size of the vector you're optimizing. And if it can't find a minima, it'll fail and just come back and say it wasn't successful. Then the full output, what it does is when you say full output is 1 or true, it will return not only the parameter that minimizes the function, but also the optimal value of that function, the number of iterations, number of function calls, and then a warning flag. That's sometimes useful, and what gets returned is sometimes a little different. For these unconstrained problems, they're all pretty close to the same, although you might get additional things returned. So here I call opt.fmin on the Rosen function. Now the Rosenbrock function, as I said, is defined in the optimized package, so they're available for testing, basically. And I just start at 0, and then I see if something happens. So I'm going to basically try to stop this. PDB set trace to stop this script when it runs. And I'm going to run unconstrained, and sure enough, it is successful and takes 165 iterations and gives me the result. You can see the value. If I hit continue, it's going to just successively try some of these other methods. So the PAL method, look at it. It's called exactly the same way. Instead of fmin, you say fmin underscore PAL, and you give it the function, the same kind of function, same calling signature, start at x0 again, and then also full output equals 1. A few different things are returned from fmin underscore PAL. There's another variable that's basically a Hessian approximation, I believe. I'm not actually entirely sure. We'd have to look at that again. The doc string for fmin underscore PAL is a little bit dated. And then, so I can continue that, and it'll do this one. Let me put another set trace there. Actually, let's continue on. And then I'll just look at the output of this so we can talk about what happened. You can compare basically the PAL method on this particular problem with the Nelder-Mead simplex method. It's hard. You can't really read too much into, you can't make general statements because of the behavior of these optimization problems on one problem. It just means that in this problem, for that starting position, fmin, the Nelder-Mead simplex method, only took 165 iterations and 289 function evaluations, whereas the PAL method took only 26 iterations, much fewer iterations, but also many, many more function evaluations. But it did get a better result. The value, the minimal value found is much closer to 0. But it really depends on the accuracy you require as to what is the kind of, how good the return value is. The other thing to look at is fmin PAL. How does it define? It has similar xtol and ftol, max iterations, max function evaluations, and so forth. I will point out this here that there is basically two flags that show up in several of these optimization algorithms. One is ret all, meaning return all, and then callback equals. The return all flag will basically provide you all of the vectors, basically the direction vectors that were found. Let's see. Actually, it gives you a list of all the solutions at each iteration, so it gives you the x values at each iteration, so you can kind of see this progress of the optimization's iteration if you want to see that. So that's sometimes useful to, if you're trying to figure out your landscape, trying to understand why an algorithm is failing and why another one might be useful, or perhaps how you could tweak an algorithm or tweak your function in order to improve the iteration or improve the optimization. The other thing is the callback equals none. Callback allows you to provide a function, a user-supplied function, which will be called after every iteration. So essentially what this allows you to do is you could set up a callback to store away the current parameter vector in a dictionary, or you could do something with that callback. You could put it in a file, put it in a database, maybe just plot it. Whatever you want to do during the iteration as it's progressing. Perhaps even do additional calculations that modify the function, I guess, if you want to have a function that is changing based on what parameter vectors are being passed in. I can't think of an application for that, but perhaps your function's dynamic and it has to read from web pages based on what the parameter vector is. We have a question. For a 2D example, is it possible to plot f of x history against design variables? This is from Hugo Gagnon. So if a 2D example, by a 2D example, do you mean there's two variables being optimized on? So x is a vector of length 2. And you want to plot f of x against design variables. Sure. I guess, I'm not sure. You have a particular range? Are you looking to plot the value of f based on where the samples occurred? I'm a little unsure about what that question means. I mean, you could create, using mgrid, for example, a list. If your design variables went over -5 to 5, then you could create, let's import from NumPy first, mgrid. Then you could create x1 and x2, which are going to be matrices that contain a mesh grid of all those design variables, and then you could evaluate your function. So here I'm going to opt Rosen evaluate on x1 and x2. To do this, I'm going to have to basically make a let's see, array x1 Rosen takes a two-dimensional array. What happens if I give it? Well, I could certainly do a nested loop like this. It really depends on whether your function can be evaluated on a matrix or not. x1i, x2j for I in x1, in length x1, for j in length x2. The object is not iterable. Sorry. Range length 1 and range length 2. Why don't I just do this? For val 1, val 2, in x1, in x2. Sorry, apologize for the delay. Val 2, or val 1 in. Sorry, I need to review my list comprehension syntax. Get rid of the i's and j's. Okay. And now call it with a vector of length 2. All right, so really, and that will generate this a nested list of output values that I could then plot. Of course, it's pretty large, so I'll not print them all. Or show, so that I could then show that with an IMShow. Something like this. AV equals array vowels, AV shape, 100 by 100. Oh, of course it is, because it, 100 by 100 returns oh, yes. It shows you actually how hard it is to do two-dimensional list comprehensions. Basically, I've got an array. It's calculating an array for each value. If I give x1, x2, and just pass it that as list, perhaps that's sufficient. Close all, and IMShow AV. That's probably more than you wanted to see. But that's the sort of thing you could do to evaluate. You basically take your function and you evaluate it at all the at all the points that you want to evaluate on, and then show it with an image. All right, and the problem here was me understanding how the Rosen function, what it did with array inputs. And so I suppose I could have looked at the source and tried to figure out its sums along axis equals 0. So as long as the array, as long as it constructed a 2D array, the as array of the input, x1 and x2, look at that shape, it's 2 by 100 by 100, and so the sum along the axis should have worked correctly. And it did. It gave me a 100 by 100 result. Okay, back to our slide presentation, or back to our demonstration of constrained optimization, or unconstrained optimization, excuse me. So Powell's method and FMIN are your two workhorses that don't require any gradient information. When you get to the Broyden-Fletcher-Goldberg-Shano method, it requires a gradient at each iteration, and it basically tries to keep track of a local Hessian and does a simple Newton step at each iteration, keeping track of a local Hessian that it's building from scratch, and it resets that Hessian if it gets to places where the Hessian is really a maximum or it's a saddle point. It'll try to reset that Hessian and just do something else until it gets near a place where the Hessian is positive definite, and so near a minima. And so the Hessian can be returned from the BFGS algorithm. You don't have to give it a gradient if you don't have a gradient, and it will, if you don't give it a gradient, approximate the gradient at each iteration. So you can see here in this call to BFGS, I'm just calling fmin underscore BFGS and providing the op.Rosenbrock function as before, and this is called exactly the same way, but internally it's going to be using a gradient calculation. So when I ran the unconstrained problem, let's make sure I've gotten rid of my PDB. It did not. Let's get rid of the set trace. Doing all of them, and go back up to the Broyden, the BFGS method. You can see that even though I didn't provide a gradient function, it did do gradient evaluations. Now, inside of those 46 gradient evaluations, effectively it had to compute the function many, many more times. And so there are 231 function evaluations that that basically occurred each time through. And it did get close to the optimal answer of 111. With this is the final result. The actual optimum is 0, and this is pretty close to that. And also I'm outputting and printing the gradient computed and the approximate Hessian that was found. So that's fairly useful. The next example just uses an exact gradient. So to see how you call it with the exact gradient, you just call the same method, fmin underscore BFGS, but also now provide f prime and set that equal to a function that calculates the gradient. So this function needs to return a vector, while the minimization function, the function you're minimizing, only returns a single scalar. The gradient function needs to return a vector or an array, a 1D array of numbers, one number for each element in the parameter vector. So if I'm minimizing with respect to two variables, my gradient function has to return two values. And Rosen-Durr does that. If I look at what Rosen-Durr returns for a particular set of inputs, it returns an array of outputs. So that's the partial derivative with respect to the first variable and the partial derivative with respect to the second variable of that underlying function. That's what you have to provide. And if you give it, then the BFGS algorithm will use it as it proceeds through its iterations. And in this case, we look at the exact gradient performance, and you can see that it only was required to call the gradient 34 times. So compare the 29 iterations with the 30 iterations, and it got a better answer. The value is now closer to 0, and the value is a little bit more optimum. So depending on how long it takes to calculate the gradient, it pays to provide the gradient to the BFGS algorithm if you can provide it relatively easily. So that's the BFGS algorithm. The conjugate gradient algorithm, the CG algorithm, fmin underscore CG, actually works very, very similar to the BFGS algorithm. So it doesn't build a local Hessian approximation, but always computes the local Hessian based on the previous answer. So I guess it does approximate the Hessian, but it uses the conjugate gradient method to iterate between directions, to find the direction. It picks the direction that's conjugate to the gradient, essentially, which tries to get closer to a local parabola minima for a general ND problem. So in this case as well, it uses the gradient and then computes the conjugate gradient, but it either uses the gradient you provide or it estimates one. So if you don't provide one, then it's called exactly the same way as fmin, fmin-pal, and fmin underscore BFGS, fmin underscore CG, and then op.Rosen. You provide the initial conditions again, and full output equals 1. And it returns, potentially, if you say full output equals 1, it returns all these different values. If you don't, it just returns the result. So it can be as easy as calling fmin CG. I'm just going to provide the function, whatever you insert your favorite function here, op.Rosen, and then a starting point. And then the return value, if I don't say full output equals 0, it equals 1, it just returns the optimal value for me. So this is how you might call it. It does print, and you can turn that printing behavior off. If you look at fmincg, it has a DISP command, or display. It's set to 1 currently, and you can set it to 0, basically, if you don't want to print that convergence information. So disp equals false, and then it doesn't print that information, and you just get xopt if it converges. If it doesn't converge, then you basically get an answer that doesn't make a lot of sense. So I don't know if I can fool this into not converging by starting somewhere perhaps really funny. No, it's still converged. So I have not played to see if I can find a funny spot in the Rosenbrock function. Perhaps one of you know of a funny spot where that would prevent convergence for this algorithm. So that's the sort of thing you can do quickly. And I illustrate that just to point out you don't have to return all these different values if you don't want to. It can be as simple as just a single call wrapped around a function of your creation. Now the nice thing about all these optimization methods in Python is that this function, which I'm here illustrated as opt.rosen, it can be whatever function you want. And that function can do anything that Python can do. It could go to the web and download something. It could wait on a socket and listen in on variables coming in. It could read data from a file, from a database. It could solve a partial differential equation. It could do some image processing calculations. Whatever you can do in Python, that function can do. All that's required is that whatever you do, you take some inputs, some vector of input, a 1D vector of input, and then return a single number as output. And in between, the optimization method doesn't care what you do or how you got that number. If you wanted, you could just, I guess, poll a bunch of websites and get a random number, and then see if the optimization algorithm would do anything with that kind of information. Okay, approximate gradient. So we've talked about CG with both an approximate and an exact gradient. We could run this unconstrained again and look at the output of the constrained, the conjugate gradient algorithm. And you can see that the iterations with the exact gradient actually went up, and the answer basically got a little worse, which is a little interesting, but not necessarily surprising, given that sometimes these methods that use, sometimes that happens. That can definitely happen, because the approximate gradient adds a little bit of almost a regularization to the problem, where you're sort of jumping around a little bit, and so you can often get the algorithm in a position where it'll find a better answer. Really, these are really so close to each other that I wouldn't say one is better than the other at this point, given the other variables that typically show up. But that can happen, and so it's useful to illustrate that just because you provide the exact gradient doesn't mean you're going to get a better answer. But I do think it had fewer function evaluations. All right, finally, the last method in the unconstrained problem is the approximate, is the Newton conjugate gradient method. The Newton conjugate gradient method requires it's fmin_ncg, and it requires you to pass in the gradient. So this, every time through, will calculate the Hessian, and because it does a numerical approximation of the Hessian based on the gradient, it requires you to provide the gradient so that it can just do a finite differencing on the gradient rather than, it could be written, this algorithm could have been written to not require the gradient and do second order finite differencing to approximate the Hessian each time through. But it wasn't written that way, so it does require the gradient information. And it, every time through, actually calculates the Hessian matrix. And if it's positive definite, it goes right to the solution. If it's not, changes, does something different to basically make it positive definite, to jump to a different place and hopefully find a location where it can get closer. The fmin, this Newton conjugate gradient method, is really a method to apply at the end of your optimization steps. Basically, because it uses the Hessian sort of exactly, it can get caught up in places and not converge as well if you start from anywhere. If you're in a particular saddle point, or at a particular saddle point in particular, and you try to use the fmin ncg, the Newton conjugate gradient method, it can fail. However, if you are very close to the optimum already, this can be a final iteration that one could apply to try to get an answer that's even closer. So the approximate Hessian, I've just got two uses of fmin underscore ncg. One is with an approximate Hessian, and one is with the exact Hessian. So the approximate Hessian uses Rosen underscore der, the gradient calculation the Rosen will do, and the exact Hessian uses Rosen underscore Hess. There is a Hessian function, an exact Hessian function inside of the optimization toolbox as well for testing this sort of thing. And fmin underscore ncg will run. Notice that with the exact Hessian, I actually couldn't start from x0 equals 0. We'll illustrate that. So when I run unconstrained, with the current starting positions, the approximate Hessian and the exact Hessian give different results, but they started from different locations. The approximate Hessian actually succeeded, and it gave me a pretty good answer. The exact Hessian gave me a really good answer, although Powell's method turns out gave me the best answer of all of these. The value was the very, very smallest, although the difference between 8.3 e to the minus 23 and 9.5 e to the minus 21 is pretty small. Look what would have happened if I would have tried to call op.fmin ncg starting with Rosen and starting at 0, 0, 0 and given it f prime equals opt Rosen der and f Hess equals opt Rosen Hess. So I get a behavior like this. It says that it terminated successfully, but the current function value is 2. The iterations were 1, the function evaluations were 2, and the gradient evaluations were 1. Basically did one Hessian evaluation, one iteration, and it's basically I think it's fair to characterize this as a bug in the NCG algorithm for when you provide an exact Hessian and it starts at a position that's basically a saddle point or a position where I'm actually not sure what the exact problem here is. I haven't investigated. But if I call the Hessian, I get that. And if I call the derivative, I get that. And I'm not sure why I decided to stop. I wonder if it could be as simple as floating point error. Yeah, looks like that's the problem. So that's a useful illustration, actually. It's basically because Rosen-Hess and Rosen-Der are functions that return integer arrays, and inside of the algorithm are calculations done that expect floating point arrays, and so the calculations were done with integers, and we get an error. If I start instead from a floating point 0, then I get a more reasonable solution. So that is a problem. It's still probably I could consider it to be a bug in the Newton conjugate gradient method, that it really should handle integer arrays because they're easy to enter, as we just saw. All right, so that was fun. We found our problem, and let's go to the unconstrained now. Any questions on constrained? The constrained problems are nice, or the unconstrained problems, excuse me, are nice, but they're typically the more interesting problems you encounter in day-to-day life are actually unconstrained problems, or excuse me, constrained problems. They're optimizations that happen under constraints. Now, one approach to that is to ignore the constraint, solve the unconstrained problem, and then see if your answer is in the feasible region. And if not, jump to a position in the feasible region and try to find a local minima there. You can get quickly tired of that unless you only have very, very simple constraints. It's useful to do an overview of the constrained methods in SciPy. Two of them, there's basically 4 algorithms we're going to talk about: an adapted BFGS method, a truncated Newton code, a constrained optimization by linear approximation code, Kabila, and then sequential least squares programming, which is a new addition to SciPy that it actually turns out to be the only function that solves the complete constrained optimization problem that's currently in SciPy. The other methods only solve subsets of the problem. The 2 truncated Newton code and the L underscore BFGS underscore B codes. The L stands for limited memory and the B stands for bounded. So these two only solve the constraint problem where you are optimizing a function subject to bounds on your input variables. If you look at the definition of the constrained optimization problem, you can see there's basically three kinds of constraints: bounds, equality constraints, and inequality constraints. The two methods shown here only allow you to have bounds on the constraints. Kabila also allows you to have inequality constraints. And the sequential least squares programming is the only one that allows both inequality constraints, bounds, and equality constraints. Now, if you have simple equality constraints, you can basically always construct a reduced problem where you essentially solve. If you have an equality constraint, then you have more parameters than you actually need. You can just solve potentially the equality equations for some of the parameters in terms of some of the other parameters. In fact, you could use optimize.f solve for that purpose in a dynamic way if you want. So let's illustrate how that might be done. I'm going to solve a constrained problem with equality constraints and inequality constraints. It's basically a portfolio optimization problem. I forgot I had a slide that illustrated it. This portfolio optimization problem, I'm maximizing the following matrix equation, a vector x. This is assumed to be a column vector, so x transpose a row vector, and x transpose times mu gives me, which is another column vector, gives me a number, a scalar. So x transpose mu minus kappa times this quadratic expression, x transpose gx. Now, it's portfolio optimization if your mu's are your returns, the expected values of the returns you're going to get, and you're basically, and the x's are percentages, basically the percentage you're going to invest in each instrument of a portfolio, and mu's are your expected returns, and then g is your expected covariances, so that quadratic expression, xtgx, is the expected variance on your portfolio. So a portfolio is a combination of instruments and percentages on those instruments. The fact that these are percentages are described by that equality constraint, all of the x sub i's sum to 1, and they're all bigger than or equal to 0. So here I have both an equality constraint and an inequality constraint. And so based on what I just said, we could technically really only use the sequential least squares programming function to solve this problem in SciPy. Well, it turns out that the equality constraint is pretty simple to solve for x3 in terms of x1 and x2. And so I could just solve a reduced constrained problem and then get my answer for the third problem just from the equality constraint. And that's a general technique that, however, as the equality constraints get harder to describe, you have to resort to numerical root finding solutions, which adds an additional layer of complexity to the optimization. So this is why it's very nice to have the sequential least squares programming method available in SciPy now, which allows you to build in an equality constraint to your optimization problem. So going to the demo, I have this implemented here in a constrain.py file. I'm maximizing this vector expression. So if I'm trying to maximize that, in SciPy everything's a minimization problem, and so I just negate. I put a negative sign in front of the function that I previously wanted to maximize, and that provides me a function I can now minimize. So I minimize the negative of that, and then x is the percentage to invest, mu is the vector of expected returns, g is the covariance matrix, and so forth. It's not particularly important, except for those who perhaps might be interested in applying this to improve your 401ks or portfolios if they've taken a hit from the previous year's financial turmoil. It's not necessarily to know what these are doing, other than to understand here's a function, here's an equation that I'm trying to minimize. So here's my objective function, and it takes x, which is an array, a vector, a 1D array of parameters, and you can see I'm going to initialize it with 3 parameters, so I'm thinking about this as a 3-dimensional problem. And then it takes a vector of mu's, a vector of a matrix G, and then this scalar kappa. The very first line of this, I'm just converting these to matrices with the mat function in NumPy. That's so I can use things like multiplication. A star is matrix multiplication, so the equation reads a little bit better. Then notice value will be a one-by-one matrix. It'll be a scalar, but it'll be a one-by-one matrix. Value.item selects out the scalar value of that matrix and returns it as the objective function. So this implements the function I'm trying to maximize, or minimize in this case. Now, I'll need the gradient for some of these problems, so I compute the gradient here. And you can see it's fairly simple. And the gradient returns an array instead of a single number, and so I use the A method of matrices to get an array back, and then I squeeze out all the dimensions that are 1. So here are my parameters I'm passing to these functions. X0 is my starting position, 30%, 30%, 40%. My expected returns are 10%, 3%, 7% in the different instruments that these represent. Kappa is basically a weight between, am I risk averse or am I looking to maximize profit? Because I'm trying to maximize the expected return, but then subtract off the variance. So a portfolio with high variance is going to weight negatively depending on kappa. So kappa is a number between 0 and infinity. The higher it is, the more conservative I am, the more I want to heavily weight risky investments. So G here is a matrix, a covariance matrix showing both the variances of the investments along with the covariances, how they're related to each other. So I just made these numbers up, so it's not that meaningful. A better example perhaps would have read from the stock market and perhaps computed historical returns and historical covariances or historical G matrix and tried to use that to estimate how good a particular index fund is going to do in the next little while and what my percentage of investments should be in order to maximize my return, assuming the future is like the past, which is, of course, not true, but at least gives me a place to start from. So how do I call, given I have this objective function, how do I call Kabila? Well, if you look at Kabila, remember that Kabila, well, let's actually go not to Kabila first. Let's go to the LBFGS and truncated Newton code. These codes, if you recall, so let me actually move this quickly, just copy and paste this down to the results, Control X, just so I talk about these in order and don't keep throwing myself off. Okay. So if you recall, this constrained Broyden BFGS method, it only can take bounds. And so the bounds are provided as a list of tuples with a lower bound and an upper bound, where any of those could be none if there is no bound on that particular dimension. So here the other thing you'll notice is this method doesn't take equality constraints, so I essentially have to construct a reduced objective function. And so I'll actually need that here. I'm going to construct this reduced objective function, and that's what's actually going to be used inside of the method. So bear with me just a little bit. So this is how I'm getting around to the problem of my not having equality constraints and wanting to use this constrained optimization method. The reduced objective function takes a smaller dimensional problem, a two-dimensional problem, and you can see it just constructs an array out of that. It makes a new vector that's one bigger than the old vector, and then copies everything into the new vector, and then for the last element, it just takes 1 minus the sum of the previous values. And so I'm automatically satisfying that constraint every time I do this problem. You can imagine doing this anytime you want to use some of these other methods without an equality constraint. You can do an equality constraint problem just by solving these problems, just like this. So you might have to use fsolve, however, to actually find the roots of the equality constraints, and that would be an optimize.fsolve. So optimize.fsolve, find the roots of a nonlinear function, and I won't talk more about it, but if you have questions, feel free to ask them, or ask them on the SciPy user mailing list, or email us if you are a gold subscriber to EPD. So the bounds here are just given as a list of tuples. My bounds they're constrained to be positive, and so I put that by putting the bound to 0, and then an upper bound of none, meaning there is no upper bound. And then I call the fmin underscore L underscore BFGS underscore B for limited memory bounded BFGS problem. And the reduced objective is the function I'm actually going to optimize. Notice I only give 2 of the elements to start with because it's a reduced optimization problem. The other arguments to the function are passed in as args, this mu and the g and the kappa variables. And the bounds equals bounds I pass in. The BFGS method needs the gradient, and it's the way this is called is a little bit different. If I want the reduced objective function only to return the function value, then I have to provide approximate gradient equals to true. So I provide approximate gradient equals true, and then I get the result, and I'm just going to print the results. For the exact calculation, it's different in that if I don't want to approximate the gradient, want to provide it, then I actually have to pass as the first argument to this constrained BFGS method a function that computes both the objective function and the gradient. And so they both have to be calculated and returned with the same thing. So every time through the loop, it's going to call this one thing and expect to get both the function and the gradient if I don't have approx grad equals true. So that's the interface there is a bit different than with the BFGS method in the unconstrained problem. But this is how you might do that. Here's a reduced objective gradient function. You can see it does exactly the same thing and computes the objective. But for the gradient, it not only has to compute the gradient, which is provided above, but it has to modify the gradient to take account of the fact that my actual objective function has this other constraint sitting on it. Basically, it's these 1 minus. So I have to add use partial derivatives, use the chain rule basically to figure out what that gradient is, and use the final gradient to compute it. So I get an analytic gradient, and then I can call the BFGS method with that objective gradient. When I run the constrained problem, you can see that it runs through and converges. We have first the output of the BFGS method. You can see it's outputting several things here, actually, and says the optimal result was reached. And there's my optimal percentages, 42%, 20%, and 37%. Of course, where optimal is completely defined by the kappa and the particular covariance and the risk, return, and the covariances of my values. And it gives me some more additional information, the gradient of the output, the number of function calls. The exact gradient also gives me an answer very, very close, very, very similar. The value is just a little bit bigger, actually, when I provide the exact gradient. But it also gives me an answer very, very close. So the truncated Newton code, again, for all of these, you can call and look at the help to see other methods, other input arguments to be provided, and so forth. The truncated Newton code is interesting because it allows you really the same thing. It's got a few more keyword arguments you can provide to control. The calling signature is much more similar to, I guess, fmin BFGS. You can provide an f prime function, which is a callable that calculates the gradient. If it's none, it actually expects the same thing as the fmin underscore LBFGS underscore b does, and that is a function that returns both the function and the gradient. And so that's how I'm going to call it in this example, since I already have that function that returns both the function and the gradient. So I call it in exactly the same way as the fmin BFGS, but now it's using the truncated Newton code, and I'm going to print the result. Notice when I print the result, I'm actually printing the total portfolio percentages by calculating, taking the actual 2D result and adding 1 minus the sum of those two values to get the final vector. So we saw that the truncated Newton code also produced an answer that was very, very similar. Okay, so that's useful. Let's look at the Kabila. Kabila has a little different calling signature because the Kabila function, if we look at its calling signature or help string, it takes the function to be minimized, it takes the parameters, the initial guess, and then it takes a sequence of constraints. These are all inequality constraints. And so the Kabila method, as I said, doesn't handle inequality constraints. Notice it also doesn't allow us to have bounds explicitly. So any bounds I would have to translate into inequality constraints. So those inequality constraints are a sequence of functions. I'm providing that sequence of functions here with just lambda expression. So this list comprehension is generating a sequence of functions. All these functions do is return the argument, the ith value of the argument. The argument passed in, of course, is the vector x, and all I'm going to return is the first value of x for the first constraint, the second value of x for the second constraint, and so forth. And those constraints I pass in as the constraints parameter to fmin Kabila. And then there's also a constraint args function. You can have a different set of arguments passed in, extra arguments passed to the original function as to the constraint function. And so I'm passing those in separately as const args. Okay, so when I call it, you can see that it basically gave me a very, very similar result. So you can see that the constrained minimization problems, there's several different ways you call them, and they all have benefits, basically, depending on what the problem is you're trying to solve. So Kabila here provides me an answer that's also very good. All right, the final constraint method we want to talk about is this newer addition to SciPy, sequential least squares programming. I'm very excited this is here. This allows us to have a single function that handles the full constrained optimization problem. And it's called, let's look at the calling syntax before we look at my demo of it. So we look at this, and it's actually the most complicated calling syntax, potentially. The only things you have to provide are the function and the initial guess. That would be the case if you didn't have any constrained problems. So I guess that means I could try to call it on my Rosenbrock function. I haven't tried this actually, so this is a live experiment. Yeah, and it actually raised an error. I wondered about that. I believe you have to give it constraints if the constraints exist. Like you can't use this to solve unconstrained problems. And perhaps there's some editing that could be done to the file. There's just little bugs in the file that would solve that problem. But so even though it says in the help string that by default it has no equality constraints and no inequality constraints, my experiments have found that you have to have at least one equality constraint and at least one inequality constraint, or else it doesn't work and gives problems. That could just be a bug in the code currently. So here I'm going to solve the problem I have, which has both equality constraints and inequality constraints. One thing to notice is I can now minimize my actual objective function instead of my reduced objective function. My equality constraint is right here. Let me actually put that on another line so you can see it by itself. So you can see the equality constraint takes the same arguments as my objective function, but just returns something that must evaluate to 0. So in this case, it returns the sum of the inputs minus 1, and so that should be 0. And then the constraints are exactly the same kind of constraints as before, except now the constraint equation expects to be given both the parameter and all of the arguments, input arguments. And so you see that it just returns the arguments. So those all have to be positive, and you pass those in as the IEConst method. Now I also pass in the bounds here. The bounds have to be between 0 and 1 because they're percentages. And then the extra arguments to pass in are given here. If I don't pass in any gradients, oh, thank you, did I make a mistake like that? Thanks, somebody helped me. Oh, thank you. That actually was quite nice. Yeah, that's correct. A little brain error. I needed to pass in the Rosenbrock function, not the Rosen derivative function, which returns not a number but a gradient. So that's actually much better. That's what I expected to have happen. What I was finding earlier in my experiments is that I couldn't, when I put an equality constraint and when I put inequality constraints, I couldn't provide just the f. I had to change the way I provided f prime. It gave me some errors earlier. So I guess the statement is your mileage may vary as you explore with this. And if you explore and find some problems, ask for help on the SciPy user list or experiment with the different parameters once you're providing to this minimization routine. Okay, so this did a pretty decent job of actually that unconstrained problem, which is nice. So back to the constrained problem, when you have these constraints, this sequential least squares approximation method actually uses the derivative information, and if you don't give it the gradient information, it will try to approximate it. Now it needs gradient information for actually the actual objective function, as well as the equality constraints and the inequality constraints. So it's going to approximate those in this first case when I run the constraint problem. And you can see that even though it approximates those, it did a pretty good job in only 3 iterations of coming up with an answer that was pretty good. In fact, better than the answer obtained when I used exact gradients. So that's, again, for this particular problem, that's something that's emerging. So it might be something you want to experiment with in your own problems. Whether or not you provide the exact gradient doesn't necessarily mean you'll get a better answer. Okay, if I go to the exact gradients, notice I'm providing not only a gradient function as f prime, so this is a fairly nice interface. The f prime is provided just as another function, and I also have to provide f prime, or can provide f prime, for the equality constraints and the inequality constraints. In this case, those derivatives are constant. That actually could be one of the reasons that the gradient, the iteration terminated so quickly as it did. So these are constants. They don't really depend on x, but I'm providing them as lambdas. And the help is pretty good, as docstrings go, on this sequential least squares programming function. It's fmin underscore. It gives you at least an idea of the kinds of parameters expected and what they should be. In particular, it shows you if you're providing the derivative information, the gradient on the equality constraint or the gradient on the inequality constraint, the shape of the array needs to be. And it has to be the length of the equality constraints times the length of the parameters. That's very useful to pay attention to the shape of the array returned. Okay. So that's the demo that I wanted to go over, and I went over it probably excruciatingly painful detail for some of you. But this code will be available in the directory associated with this video after the webinar is completed, and you can go back and look at it and use it for examples in your own work. And that's one of the reasons I went over it so carefully. That's basically all I have today. If there are any questions, I'm happy to take them now. I do want to remind people about our Python classes. We have another open class in May and August. I believe those dates are correct, but they may be updated. May need to be updated. There are 2 3-day and 5-day options. Basically, you can take the 3-day course, which is the Python for Scientists and Engineers, and the 2-day option is a wrapping, interfacing, and traits UI, or basically building user interfaces, GUI interfaces with Python. You do have to have taken a 3-day course to take just the 2-day option, however. Oh, here's a question from another question. Thank you for the question. Are you planning to implement genetic algorithms? That's a great question. That really gets to something I really hadn't covered in this webinar at all, which is the global optimization question. So there used to be inside of SciPy a genetic algorithm. It lived in the sandbox. It was imported as scipy.ga. It's not there anymore. It currently lives in an old version of SciPy in the sandbox, and it's code that Eric Jones wrote while writing his PhD. And it's a pretty good genetic algorithm. I would love to see another genetic algorithm inside of SciPy. I'm hoping we can get another contribution. Basically, the genetic algorithm that Eric wrote, it fell out of maintenance, and it wasn't maintained, and so it kind of removed from the sandbox. So I guess the answer to that question is I'm not currently planning to do that. There are others who have genetic algorithms. They're not living in SciPy now, and my suggestion would be to go to the website. Well, 2 suggestions. One is to go to scipy.org and just look around. You've probably already done this, though, but Google can be your friend. Genetic algorithms and Python. And you may actually find something like PyGene and some recipes on ActiveState. I would love to clean some of these up and actually provide a genetic algorithm interface in SciPy as well. The other thing I'll mention briefly is there is another package called OpenOpt. And OpenOpt at openopt.org is written by a gentleman in Russia, and it used to be a scikit, but now it's not a scikit anymore. It's his own OpenOpt framework. And it basically provides an interface to all the SciPy optimizers, and then it adds a couple of additional optimizers, like Rauge. I guess it says lots of others as well. So you can look and see what those problems are. There's a few linear problems, quadratic problems, second-order cone problems. So you can see that it kind of specializes the optimization problem in some cases And then the mixed integer linear problems are interesting because you constrain the values to be on the integers base, or on Boolean problems. So if you are encountering problems like that, I would encourage you to look at the OpenOpt. And it's a freely available package as well. It's BSD licensed, just like SciPy. His development cycle, he wanted to be faster than what SciPy could provide, as far as I'm aware, and that's one of the reasons it's not inside of SciPy as it is. But it's a pretty good package, and I would suggest that you check it out. I can't comment any more than that. I haven't used it myself in anger or in earnest. So genetic algorithms, sorry, it's not. I can't point you to something besides Pygene, but I appreciate that question. Well, any other questions? Well, thank you, everybody, for coming then. I appreciate you taking time with us today and staying with us through the little bit of technical difficulties at the front. Join us again for our next webinar next month, our next MTOP Python distribution on April 2nd. Oh, thank you, Amenity. It's going to be 3D visualization. You can go ahead and speak up. I think they can hear you probably. That would be great. 3D visualization, and hopefully we'll get somebody who can present some useful things on Miyavi. All right, thanks, everybody. If there's no other questions, we'll see you next time.